Our sponsor today is Principal Solar, who is building a distributed solar utility through acquisitions of existing solar installations and permitted new development. If you own solar assets in the 5 to 100 megawatt range, please visit www.principalsolar.com to learn more. And our presenter today is Matt Roberts. Matt serves as the Executive Director of the Energy Storage Association with over 12 years of experience in energy policy, communications, and association management. He's a recognized expert in renewables, distributed generation, and sustainable infrastructure. Before ESA, he oversaw policy and operations for a global energy trade association, which was focused on reforming the transportation infrastructure and expanding the use of renewable fuels. Matt started his career as a House staffer and speechwriter, and he's consulted in the energy industry with organizations focused on solar, wind, and geothermal energy policy and deployment. He has testified as an expert witness for the U.S. Congress, and he's spoken at conferences around the globe on energy policy and sustainability. And so with that, I will turn things over to Matt. So, Matt, you can begin.
Great. Thank you very much. Definitely appreciate the introduction, and thank you, everyone, for joining us. I see a lot of familiar names on the attendee list, so looking forward towards the end here to be able to answer everyone's questions and have a pretty thorough discussion. Since I'm not necessarily familiar with everyone who's on the call, what I wanted to do today was really give a kind of primer on energy storage, talk a little bit about the technologies that are out there, dig in a little bit on some of the applications, how storage is used on the grid and also behind the meter, and then do a little more focused at the end on solar and storage combined, or more broadly, renewables and storage combined, where some of the opportunities, benefits, and other variables are in that equation. So, one of the things that we've been doing when I get out and talk about storage with new audiences is trying to address some of these perceptions that are out there kind of head on. As the title of today's presentation alludes to, a lot of times when we think about storage being paired with renewables, the focus really comes on to this on-demand concept, how to make a renewable on-demand as a generation resource. But that's one of the things that we kind of want to broaden that concept a little bit. There is that potential, but there are also a lot of other things that storage does, especially when we start looking at system-wide benefits, and we'll dig into some of that today. Really briefly about the Energy Storage Association, you should see here just kind of a list of some of our members. This definitely isn't inclusive of everyone, but it does give you kind of a sense of some of the people that we work with. So it's really broad spectrum, all the way from technology startups to multinational manufacturers, financial, legal, and across the spectrum of technologies that are engaged in energy storage. Just as kind of a really big picture, this is looking at grid-connected energy storage projects around the world. There are projects all over the world. You can definitely see the concentrations in North America and in Europe, but also in Asia, a number in South America, some in Australia, some of the Pacific Islands. So projects of all sorts are getting out there. And this chart, includes a number of the different technologies that are out there. I wanted to give just some quick rundown on some of the technologies. Wanted to give diagrams because I figure this audience may be most familiar with looking at these technologies this way. So, battery energy storage systems. In this one, this just says kind of storage device. So there's a number of different electrochemistries we could be talking about. Kind of how a system would be set up. This gives a little sense of that. This is from Sandia National Labs. But battery energy storage, definitely one of the items that is focused on often, but not the only technology out there that is used for in storage applications. Redox flow batteries is another one. There's a number of great companies working in the redox flow battery space. For those who may not know, the simplest comparison, but it may be even a little too simple, is flow batteries are often compared to fuel cells. That's not 100% accurate as a comparison, but it does kind of get you in the right mindset for how these technologies work, where you have a liquid electrolyte kind of flowing through the system. One of the great benefits there is it allows you to scale very easily for some of these large-scale, longer duration applications. One technology or a set of technologies that is sometimes overlooked when we're having these conversations is in thermal storage as well. Thermal energy storage, two different ways to look at it: storing heat, often done in concentrated solar projects where there's a molten salt or another substrate that's used to capture that heat energy for use on demand. And then the chilling applications as well. One of the biggest loads on our electric grid is in the HVAC sector. And so these thermal applications are great for buildings and some other interesting applications of thermal technologies. But definitely one to keep in this conversation as we're talking about energy storage. Thermal has immense capability to help reduce load and demand. Compressed air energy storage, also another big storage technology that you'll see in some large-scale deployments. There's been a couple large case projects announced recently that I definitely encourage you to find more about. Oftentimes, there's a number of different ways that this is applied, but oftentimes there are some depleted gas reservoirs or salt mines or other places like that where you can compress air and then be able to use it to drive turbines and provide generation capacity on demand when needed. One of the other technologies is flywheel technology. This is a diagram and chart provided by the guys at Beacon Power, which is a great flywheel company. Magnetically levitated, vacuum sealed. It's amazing technology and really is great for those very rapid kind of bursts of energy that are used in ancillary services and a number of other grid applications. So flywheel technology is definitely part of this as well. As a brief chart, I think that this gives some insight into kind of the multiple technologies out there. This tries to kind of make a simplification of some of the best applications for these technologies. But does give you a sense, or at least a little better sense, of how they're used on the grid and some of the places that they're deployed. I've been told that these slides will be made available to everyone after this call as well, so if I don't spend enough time on one of these slides, you can definitely download a PDF of them afterwards as well. So this starts looking at some of the different applications, so I want to talk a little bit about some of the primary applications that energy storage is used for on the grid. This is a partial list, but this is built from DOE's Energy Storage Handbook, and these are some of the services that were highlighted in that handbook that energy storage is very viable for on the grid and also on the customer side as well. So time shifting, which we often refer to as peak shifting, some of the ancillary services, but also at these kind of higher level transmission and distribution infrastructure, where there's these system-wide benefits from utilizing energy storage technologies and systems. And then on the customer side, where the customer is able to use storage technologies for demand-side management, power quality, energy time shift for time of use. And we'll focus a little bit at the end on those because I think that has a lot of applicability for this audience when we're talking about solar and PV installations. So we'll start with one of the big applications, which I think is of interest, which is this idea around peak shifting. I think this is one of the first things that people think about when talking about energy storage combined with solar and renewables, which is kind of making that generation capacity line up better when there is the highest amount of demand on the system. This is a famous chart, which you will often see when people are talking about this topic. This is very micro, though. So this chart is showing in California on the shoulder months, so spring and fall months, they start to see this as their load. And for those kind of familiar with this, you can start to see where the problem develops over time. In the middle there, that kind of fatter part, which we refer to as the belly of the duck, you can start to see that during the peak daytime hours, when solar generation is very high, it really starts to reduce that overall net load and really brings that down, which on the surface is a great thing, reducing the need for generation capacity from fossil fuels and other sources. But as you can see, once we get a little later in the day, 5, 6, 7 o'clock, thousands and thousands of people are coming home, flipping on TVs, air conditioners, settling into their house, and this peak demand ramps up very quickly. And so there is, a need to meet that peak demand. There are ways to do this through forecasting and some other things, but there still is that very quick ramp up, which means you have to put systems online very fast, and often the solution is to use a peaker plant or something along those lines, which are inefficient facilities that generate a lot of emissions and use fuel inefficiently because they're only on for a fraction of the time during the day. This is a place where storage can have a great opportunity to have a big impact on the overall system and what's going on the grid. How this works is, this is a very simplified demonstration of how something like this works. In this blue section here on the left, that is where you would put that load, basically shift that light green load to the middle of the day when you have a lot of solar capacity, you have a lot of other renewables churning out energy during the day, be able to capture that with an energy storage system. A number of different systems could be applicable for this application. And then, when needed, instead of flipping on as much peakers or any peakers during this high demand time as solar generation starts to wane in the early evening and into the nighttime, you would be able to utilize that stored energy to be able to offset that peak. And which gives kind of overall system-wide benefits. Not only are you reducing that peak demand, but that helps you with the need for expanded infrastructure that is carrying energy across during this peak demand. It allows you to not necessarily need these peaking facilities and these peaking plants. So it has kind of overarching system benefits outside of just the individual location where that energy is being captured. So this is definitely a big place where energy storage has a lot to offer. There's a lot of different resources out there that I think are great to find out more about this. One of them is, if you actually take a look at a later time at AES's Choose Storage infographic, I think there's a lot of good information there, and I highly recommend that people take a look at that. This is a big problem, though, so get into the macro scale now. EIA predicts that there's going to be 40 gigawatts of peak generation needed over the next 15 years. So increasingly, we have more and more renewables coming online, dropping that net load during the day, and then a larger and larger ramp and a larger and larger peak as to that energy intensity rises, especially as we start to bring on more things like electric vehicles. As people get home, they're going to be adding those big loads to the grid, and even more demand during those times at 5, 6, 7, 8 p.m. Some of that obviously can be controlled, at the point of charge, but that definitely is going to put increased strain and burden on the grid as we move forward over the next 15 or 20 years. It's a very significant issue that needs to be addressed, and a place that storage is very well suited because of its attributes. One of the other big services or applications for energy storage is this idea of load following and these ancillary services. I think many of the people on this call are going to be familiar with the idea of frequency on the grid, that the grid needs to be operating at a very specific frequency. If it sags too low, it can cause the grid to trip and cause brownouts and other problems. Too high, and it can be delivering too high a frequency of energy, and literally would be blowing out the sockets at your house. So this is something that needs to be managed, and to keep that frequency right in the sweet spot around 60 hertz. And energy storage is is very well suited for these kind of high intensity, kind of short duration bursts of energy that help to keep that frequency stable by following the load and what's going on the grid. So you can see this here. This is just an example of one day in the PJM marketplace looking at the regulation services signal. So the blue dots that you'll see a little bit faint, but that'll show you when the PJM signal comes into place, And then you can see this is an example with a battery energy storage system and how that system is responding. So when it's taking energy off the grid is on the low points there when it goes under zero, when it's putting energy back onto the grid to help make sure that frequency is in line and it's delivering energy effectively. Now, one of the really big benefits of energy storage as compared to other solutions for frequency response is twofold. Energy storage is a very dynamic resource, but it's also very rapid. When you use, say, a governor on a natural gas-fired plant, there is a delay in time where that governor has to be applied. It starts to change the spin rate, and then it either produces more or less power as needed. And there is a delay in that time. So during that time, 10,000 people could flip their lights on, and so it would be responding to that signal to meet that need. But while it's responding, that signal may change. It may be in a different point. So all of a sudden you could be overproducing, and then you have to compensate for that. So having very rapid, sometimes sub-millisecond response time from these technologies is incredibly valuable to the grid because it allows us to be more efficient in the energy that we're using and to make sure that we're responding to signals very accurately. So in a number of different places there are different incentives and market structures to make sure that dynamic, fast-responding resources are able to play in the grid and provide these services. But this is just one example of what this might look like. But these systems, they're very flexible. So in the same sense, when you're looking at a gas peaker to try and do some of this, this kind of segues a little bit back towards peaking plants, but these facilities are also used for frequency response. These gas peakers need to sit there online idle, burning fuel, ready to go, because they have to be warmed up. You can't kind of cold start them and just go, off to the races. These peaker plants are inefficient and also have about a 40 megawatt flexible range. When you're looking at a energy storage device, in this case on the right here it's symbolized with a battery, but this can be any energy storage system. It has almost it has 100 megawatts of flexible range because when you need it to, it can also be a load on the grid. It can be absorbing wind energy that would otherwise be curtailed. It can absorb over-generation from solar during the day, which is valuable because then they're able to get that renewable energy onto the grid instead of just allowing it to dissipate. That flexible range is very important. I would say one other note when talking about using a gas-fired plant to do these frequency regulation or load following services is that actually puts strain on those peaker facilities as well. They're not designed necessarily to do this fast-responding dynamic work on the grid, and it will shorten the overall lifespan of that multi-million-dollar asset. That's a very important thing to keep in perspective here as well is it can shorten the life cycle of those very expensive facilities when there is a more dynamic and better suited technology out there that can provide those services. So as I said before, different markets, obviously in the U.S. we have very distinct markets in very different places. What works in ERCOT is different than California, is different than PJM, between the different ISOs. So one to look at here is what's been going on in PJM. PJM introduced a second fast-moving regulation signal called Reg D, and this is another grid signal that energy storage and other fast-responding devices can tap into. And so they implemented pay-for-performance, basically as a way to reward this more dynamic, more efficient device for delivering services on the grid. And it almost effectively tripled the payment for the market clearing prices to incentivize these devices. And it went from maybe 6 or so devices on there to 19, and I think that number is more like 25 now. This chart's slightly out of date, but I think it gets across the overall sentiment here. And as you can see in the bottom right-hand corner there, where it looks at regulation requirements, you can already see that pay for performance is having an impact. It's reducing the overall amount of energy that is needed for these services. and delivering that energy more efficiently. So I think that that's definitely reflective of the value and attributes of energy storage devices, that it's able to reduce that overall demand and is already having a great impact in the PJM marketplace and other places that have pay-for-performance market structures in place. So I think that this is obviously kind of the crux. This is going to be one of the big things that is very much so of interest on this call is renewables and storage. One of the big things is obviously smoothing power output and helping to smooth that intermittency. That is a great value that storage can bring for some of these large installations, these grid-connected installations. It also, when we start talking about system-wide benefits, storage systems prevent large local spikes that can be caused from renewables. If you have a lot of distributed renewables in one area, cloud cover coming over can cause a big sag in how much energy is being put off, and then it will ramp back up again as those clouds pass over. Energy storage can help mitigate those issues that are caused by high renewable penetration. And not only can it mitigate those issues, but it also enables renewables as well. Having storage devices throughout the system also enables you to have more renewables on the grid, which I think is, obviously a positive in terms of carbon reduction, but, obviously a positive for this group as well, as many of you are solar developers and installers. It creates greater opportunities and allows us to hit those higher penetration points where we start to see some of these system impacts from high renewable penetration. Storage can enable that. So, it's not necessarily this concept of a 24/7 on-demand solar. There are system-wide benefits that are provided by energy storage that go beyond just that one concept, which I suppose you would kind of place in the peak shifting or time shifting category. It goes on and provides a number of high-level benefits. Just for a quick system design, this is a nice infographic that I borrowed from the folks at Solar Grid Storage. I think that this gives a good sense of kind of what these systems would look like. Solar arrays either on the roof or pole mounted on the ground. Solar Grid Storage uses a battery system they call power factor. But then you can also see in there that you would have your solar meter, which would be measuring your RECs and keep track of your solar RECs. You'd have your distribution panel for the building, and then outside of that, you would have the utility net meter for folks that are doing net metering, and also just to measure the amount of energy that's going back onto the grid. With that device, either residential or in this case, it looks more like a commercial or industrial customer would be able to leverage that stored renewable energy to use it at different times. And there are things along the lines of time of use rates, which are becoming more prevalent. We're starting to see more and more of, that you would be able to use that energy when it's needed most and when it will provide the best savings to your building, if you're on the building side, or where to provide the highest value to the grid if you're on the grid-connected side. So that opens up that flexibility to be able to either compete in markets if you're on the grid side, or to reduce your overall demand and charges and everything else on the customer-sided side. So this is just one last look at kind of that load following and that smoothing out. This is how energy storage operates kind of in real time. This is a 60-minute window that we're looking at here, and just an illustration, and kind of you can see that smoothed demand and the actual demand where storage is responding rapidly in a partial state of charge to be able to absorb and put out energy as needed. To smooth that demand. So this is looking at kind of the customer side, how you can smooth the demand from a building and kind of keep that flat even as there are spikes along the way. And this has big implications for demand charges, time of use rates, and some of those other avoided costs that storage enables you to be able to deal with and mitigate. I think that this is common perception, that this is kind of the common understanding of how energy storage systems are used. So this is looking at a time shift, basically. So, wind tends to be more prevalent at night. So, while you have that wind generation in the evening, you're able to capture that into your energy storage system, which is going to be our red dotted line there. And then as we get into the day, you're going to be doing using your storage to flatten that out a little bit and be delivering that energy during the day when it's more often needed, and be able to capture that value. So you're not needing to curtail that wind resource, which is often the case in places like West Texas, where there's immense amounts of wind on the grid. And more on the way. I think there's another 7 gigawatts planned for West Texas, so this is going to be increasingly more common way to address some of those issues. But you can see that this kind of standard time shift, which is something I know is of interest to this group, and how that would play out in real time. So a lot of this, as we're talking about this, is based on the local markets. Some of these opportunities are opened up at the FERC level, but obviously not every market is subject to FERC jurisdiction, and every state has their own needs and constructs and market designs, not just states, but also ISOs, that is important to be aware of. So I want to do kind of a step back and look at this from a very high level in terms of policy. So, in the storage sector and in any energy technology sector, policy is able to bring in capital investment and lower costs. So on the equity side, structures like pay for performance, additional kind of competitive market structures, this is really driven by FERC and the ISO. That increases the revenues that are available to profit from having these devices deployed on the grid. On the cost side, things like the investment tax credit, MLPs, master limited partnerships, help to level the playing field. Some of this is done at Congress. Some of this is done, well, a lot of this, especially the investment tax credit, which I know is something that this group looks at closely. Energy storage is eligible for the investment tax credit when it is paired in a renewable system. Currently, energy storage is not eligible for a standalone tax credit, but that is something that we're working on here at the federal level. On the debt side, for the debt and risk, revenue certainty structures like PPAs, these kind of things, IRPs, time of use rate deferral, a lot of these are subject to what's going on in the states and sort of the market designs that are there, where those opportunities can become more prevalent and help to guarantee more revenue certainty. That's done at the states and also partially at the FERC level as well. And then on the technology risk side, some of these are emerging technologies, some of these are established technologies, but there are things like loan guarantees, ARPA-E, New York BEST is doing a lot of great work, I think, in this space as well. And that kind of covers the spectrum for states, DOE, and Congress. All of them, I think, have a role to play in that and to be able to invest in some of these technologies as they're deployed on the grid. So I wanted to give some sense, because I know we get into cost quite often when we're having these conversations as well, and it really does, we need to, often we'll get focused on the individual system cost and the, kind of on-site, inside the fence costs, and not necessarily looking at the bigger picture here and what these kind of system-wide costs are. Say if you were to be putting a system in California, they have the small generator program there, or the self-generation program there, I apologize. That's $2 a watt. That can be applied towards energy storage systems. The federal tax credit, the ITC, that's 30% if built into a solar system. In a place that has time of use rates, that can be up to $500 per kilowatt hour over the system lifetime in avoided costs on time of use rates. So, with all of these things taken into consideration, a system could cost as much as $1,400 per kilowatt hour or even more depending on where it's located, and still be a break-even for investment. So, we need to look at kind of not just the individual cost, but two other factors. The cost when looking at the full ecosystem of, kind of what incentives and what market drivers are in place, but then also the system costs compared to what? what else are we comparing to a peaker facility, to other alternatives that are out there, energy storage becomes very agreeable, and those prices are on a much different scale than when we're looking at what the alternatives are and what we're competing against effectively on the grid. So when there are markets that reward storage's flexible dynamic attributes, the entire grid benefits. The grid is able to operate more efficiently, is able to take advantage of those dynamic resources, and cut down not only overall use, but increase flexibility, which in turn increases resiliency on the grid and creates a more resilient grid infrastructure. So I would think the one big takeaway from all this is that the benefits are not just there at the individual project level, but they're also system-wide. So by deploying more storage, we're increasing the system-wide benefits, or we're bringing about benefits that are system-wide. Looking really quickly again at sort of the benefits and maximum market potential, these are very much so estimates, but just to kind of put some of the scale of this into perspective, all the different services that energy storage provides, or at least a mostly complete list of the services energy storage can provide are down there. And you can see it in that kind of benefits per kilowatt over a 10-year life cycle. Some obviously have much greater potential than others, and this kind of highlights sort of the maximum market potential, where those market opportunities are. This is definitely simplified, but I think that this gives at least a little bit of perspective into this conversation. So I wanted to make sure that we allotted plenty of time for questions and answers. So I was going to go ahead and hold off right there and turn it back over to you, Rick, if you want to talk a little bit, if you want to open up with some questions.
Okay, and just a reminder to our audience, and thank you very much, Matt, for that overview. If you have any questions for Matt, please send a chat. You can chat to all panelists, and I'll read those questions out, or you can send a chat to all participants if you want to share it with the entire audience. And Matt, while those are coming in, did you want to go ahead and introduce these two events you have upcoming?
Yeah, absolutely. I know a lot of folks on this call are based in Texas or are interested in the Texas market, so I wanted to highlight two things that are coming up. Great place to continue this conversation. One is on December 5th, we're about to put out this announcement that we're going to be hosting the Texas Energy Storage Summit. I think it's a great opportunity to get people from around the country in to talk about best practices, how implementation is going in different parts of the country, and bring a focus to what's going on in ERCOT and the broader Texas markets. So this should be a great opportunity for anyone who's interested. We'll have more information available on our website. Also, our annual conference happens to be in Texas this upcoming year as well. So we're going to be in Dallas, Texas, May 19th to the 21st, and I encourage everyone to take a look at that event, for a comprehensive overview of technologies, markets, policy. There definitely is no better place than that gathering. I think that we really do get a world-class event pulled together. And I encourage everyone here to take a look at that, and if you're interested, come join us in Dallas in May.
Okay, and some questions have come in, and please keep typing those. The first question was, I didn't see thermal storage in your early slide on the global energy storage capacity by type. How much thermal storage is in use today?
That's an interesting question. I apologize that I won't have a definitive number on that, but I can follow up with the team at Principal Solar to provide at least a good ballpark estimate. Thermal storage is very widely used, though, and there are a couple different ways that we often see it. One is you'll often hear about ice energy storage, which is very much so similar to thermal solar technology. I'm a very big fan of these because it's lower cost up front, delivers great benefits right away. So ice energy storage, literally make ice at night when it's cooler, when energy is cheaper, when you may have more renewables or excess renewables, and then use that to offset your HVAC load. So there are buildings all over the country that are deploying ice energy and using that. There's also another technology out there from a company called TOS and some others that are looking at that as well, which actually uses thermal chilling to chill air as it's being injected into a gas turbine. As many may know, if you have denser air, you can get more of the fuel into the turbine, and there actually is a vampire load, or not a vampire load, but basically when it's very hot out, the capacity of a natural gas-fired turbine actually goes down because it's not able to get as much of the fuel into the system in that hotter air. So by chilling the air going into the system, you can expand its use, be able to get more capacity out of that power plant. Very important in a place like Texas that has those hot summers. But I'll do my best to get a number on kind of the volume of thermal installs that are out there and what that looks like.
Okay. The next question was, what about distributed storage? For example, everyone either has a battery or an electric vehicle in their house, and then together we have a large amount of capacity.
Yeah, this is you know, an interesting concept that we're seeing more and more people considering. I think what you're leaning towards there is this idea of aggregate storage. You know, I think that it's very interesting if you know, say a company, project developer is out there and they have, you know, 500 installs, let's see, like a Solar City or someone puts in a ton of these devices and then uses them collectively or in aggregate as a capacity factor on the grid. It's definitely an interesting angle for using energy storage. We haven't seen people doing something like that in mass as of yet, but it is a very viable thing to be looking at in the future. And you're absolutely correct. When we're talking about electric vehicles, there's a number of people that are exploring what we would say is a vehicle-to-grid energy, which is kind of twofold. One, it's a little bit of demand response, only charging when it's most appropriate on the grid. And some places are looking at incentives for customers to do that. But on the flip side, there is the potential, and there are some pilot projects out there, one of which is in Texas, I believe. I think the Pecan Street project is doing some of this, and there might be some in Dallas as well, using EV batteries to perform some grid services, like ancillary services, frequency, load following, some of those things. So that is a developing concept. You know, a bunch of different places are testing it out, but it's not something that is being deployed on a very large scale as of yet. How to get, you know, thousands of EV batteries to perform as one synchronous system.
Okay, the next question from Gordon. Do you see FR being paid similar to PJM's rate outside of the PJM service area, like in North Carolina specifically?
I apologize that I don't know what the current North Carolina rate is for FR, if they have a pay-for-performance system in place. I don't believe that they do right now. In reflecting on kind of PJM's product and how they manage it, I would imagine over time that they'll scale back that payment as more and more of these dynamic resources are on the grid. You know, in part, this pay-for-performance is intended to encourage these systems because of their system-wide benefits. So that payment, that, you know, that increased payment, you know, it's tripling the payment. It doesn't necessarily mean that it's using 1/3 the amount of energy. The increased payment is intended to be reflective of those kind of less tangible values, those system-wide values that are provided by these devices. I know that there's pay-for-performance in place in California, and they're continuing to evolve that market in California. And in Texas, actually, we are intimately involved and on the ground in the FAST process that is going on right now, which is overhauling the ancillary services market in Texas. That project is coming, or that process is coming along. It's a stakeholder process at ERCOT. And currently, they're beginning the discussions around what a pay-for-performance model might look like in Texas. So we're kind of seeing it piece by piece. It's being established in different markets at different times, and we continue to work on those to try and open that up so that that pay-for-performance model is instituted. This was something that came down from FERC, so there is a FERC order that is applied to the states and to the markets, everyone who's under FERC jurisdiction. Obviously, ERCOT falls outside of that, but most other jurisdictions are going to be putting something like this in place.
Okay. Next question was from Matt. What are some of the most successful storage projects in the U.S.? And maybe to give you some parameters, what would be the largest project, the most profitable project, and maybe one of the most interesting projects looking forward?
Well, I can definitely answer. I'll put it into context. So there's a couple different scales that we're talking about. So when we look at one technology we didn't highlight at the beginning is pumped hydro. So pumped hydro is a very large-scale technology. These are hundreds of megawatts for some of these installations, and so they are very large-scale. But pumped hydro, while it is energy storage and is a great form of energy storage, it does have its unique attributes in terms of siting and some of the regulation around how those are done. So it kind of differentiates itself from these what we would call advanced energy storage technologies. So pumped hydro projects are definitely going to be some of the biggest out there. In terms of advanced energy storage, there's a couple projects out there. It depends if you're measuring in megawatts or megawatt hours. That'll determine kind of what you would consider the biggest project out there. But in Texas, there is the No Trees project, which is out in No Trees, Texas. That is a 36 megawatt installation. It's actually lead-acid batteries. It's almost I don't want to call it a basic battery technology, but it's one that many people are familiar with. It's an electrochemistry that we have a lot of experience as the energy industry with that technology. And that is in coordination with a wind farm that is out there in West Texas, and obviously a lot of wind out in West Texas. So I would say that is the largest battery install in the U.S., one of the largest in the world. In terms of profitability, that's a hard one for me to kind of scale up, like what is the most profitable system out there. I'm not necessarily privy to all of that information, but there obviously are great market structures, as we highlighted in PJM, so folks working in the ancillary services market there are taking advantage of that. I think that there are projects around the country that are generating a lot of revenue and performing great services for the grid. So I'll decline on that one to specify who may be the most profitable. On the last one, the kind of most interesting project, I think there's a lot of really interesting projects. There's a great one coming up, a compressed energy storage project that's going to be going in Utah that the folks from Duke Energy Storage are putting in place. And they're working on now, so that'll be evolving over you'll see more and more news about that, but that's a very large-scale project. I'm always interested in flow battery technology. I think that there's some great applications for flow battery, especially in this peak shifting and some of these kind of time of use mitigation as well. If you look at, say, Enervolt's project in Turlock, California, it's the world's largest iron chromium redox flow battery, and the first one in megawatt scale. So that's definitely an exciting project to keep your eyes on as well. So I think those ones are very interesting, but there are plenty of other ones in the pipeline as well. Beacon Power has a flywheel project going in Alaska, which I think gets into some of the island issues. Islands like Hawaii or Puerto Rico and smaller as well are very susceptible to, as they start getting on more and more renewables, their penetration obviously goes up a lot faster than when you add a couple more megawatts to a system like ERCOT. They're very keen on how to use energy storage to make that power more, increase power quality and smooth out that generation a little bit. So plenty of interesting stuff on the horizon.
Okay, and it sounds like maybe you should have an event with an award ceremony with those categories at some point.
Yeah,
okay.
Absolutely. At our annual conference, we do a few awards highlighting, not just industry champions and people who make kind of a difference industry-wide, but also some of the companies that are really taking some innovative steps forward. So.
Okay, two questions from Stephen. What is a reasonable round-trip charge-discharge losses that should be expected from batteries, such as lead, acid, and flow? And the second one is, regarding scale, does smaller distributed customer-sided storage make more sense than larger substation-level, substation-based storage in terms of enabling more PV, photovoltaics, or wind?
So on the round-trip efficiency, you're going to see variation, obviously, based on electrochemistry, system design, what kind of power controls are used, all of those things, on the inverter technology. But you're going to see, ranges from 65, 70, 80% round-trip efficiency. Some are higher, have been tested at higher, so it's going to be, there's a range of round-trip efficiencies in there. So there is a energy loss when you're doing a storage device. And then on the second question, so distributed versus larger scale, what's a better enabler of renewables? I think on the customer side, so if you're putting in storage at a facility, I think that the device itself actually allows you to scale up the amount of renewables you put on a site. So if you're doing a solar install and you bring storage into that as well, that'll allow you to put more panels on that site because you're able to take advantage of time shifting and these opportunities to, it's not just the generation that you can put out at an instant, but also some of that generation you can carry over and use at very specific times to either do peak shaving or some of these other maybe higher profit services, demand reduction, as well. So I think that on the site side, that enables you to do a larger install if you're to combine storage in with a renewable technology. In terms of the overarching system benefit, I think that the larger scale is going to enable that more overarching benefit. So, when looking at the substation level, some of those megawatt plus installations, those enable more renewables throughout the grid system, not just at the specific point of installation. So the system-wide benefits that storage provides, you're able to take advantage of more when you're looking at that larger scale. So.
Okay. The next question from Rick: do you see safety as a significant consideration when customers are evaluating storage products?
Safety is, definitely something that is very important to every industry, and it's no different when we're talking about energy storage. There's different considerations based on what technologies we're referring to, I would say, though, that no, I think that safety is important, and it is something that needs to be thought about and needs to be included in the process, but I don't think it is something that should be a detriment to energy storage. It's one of those things where you can spend more money, you can raise the system cost to increase the safety, basically. If you were to, spread the cells out so they're 20 feet away from each other, you'd have a huge project, but it would be, have this undeniable safety record along with it. So, it is something that's taken very seriously, and I think it needs to be a part of any system planning. We need to be very mindful of interconnection standards. We need to be mindful of on-site, system integration, and what those systems look like. But I think that this is something that companies are addressing in their system designs and bringing a safe product to the table and deploying those products in the field.
Okay. Next question was from Will. At what point would the PJM frequency regulation markets or other ancillary service markets start to get saturated and the market prices begin to drop? Is there any advice from you on where to learn more about the medium-term 5 to 10-year outlook for the ancillary services markets?
I'll start with the second part first. So there are a number of sources out there that do consulting work in this space, that have done projection numbers on this. Navigant Consulting, CES, Green Tech Media. These are all folks who look at these market sizes and do kind of outlooks based on their own forecasting. There is an oversimplified formula, which is 1% of generation capacity is about the size of the ancillary market. And so, I think that there is, you're absolutely correct. The incentive kind of pay-for-performance structure that is in place is intended to be an incentive to get these systems out there so we have the system-wide benefits. So there will be saturation to a point that ISOs and different market structures will start to reconsider how large of a payment they're making for some of these services. And so, the early adopters are the ones who are going to be able to take advantage of these larger payments now. And as the systems become more mature, I think we'll start to see a reduction in some of those payments. I think that's a ways off, though. I think that there is a really immense need, especially if you look at a place like PJM. I mean, it's I believe it's the biggest energy market in the world. There's a lot of need right now for these dynamic, fast-responding resources. So that's something that I think will happen over time. When new market structures are considered, often they, the conversation sometimes goes to this idea of a staggered payment structure. So the first 20 megawatt hours that are on the system will receive X payment. The next 20 megawatt hours will receive Y payment for those ancillary services. But I haven't seen one of those put into place yet that is subdivided in that manner.
Excellent. Next question from Ken. Are there statistics available on storage projects that are getting underway for the California 1,300 megawatt storage initiative?
Yes. So there's definitely information that's rolling out about that now. You'll probably see some announcements, or there's some planned announcements next week about, I think, about 50 megawatts of procurement that's coming down. But you can already see in the interconnection queue in California, there is, a lot of storage kind of on the horizon. So, the California system, if people aren't familiar with the rule that was put in place, is that the CPUC and the Energy Commission have directed the utilities to procure 1.3 gigawatts of energy storage systems. And it's in a mix of scales, so some of the large scale, some of the medium scale as well, systems on the grid over the coming years. So this is definitely a driver in many ways for energy storage right now, and is a very attractive market, while there are other very attractive markets out there as well. Hawaii is doing a lot of work in this space, has a lot of RFPs out right now. Also, people may have seen some of the news in Arizona. There's a very exciting opportunity coming up in Arizona. Ontario is doing some great work, New York as well. In California, this is obviously a focal point right now. A lot of people are talking about this because it is very exciting. Yeah, information, statistics continue to roll out about what is going on there. And so, you can definitely check out, PG&E, SC&E. The utilities are putting out information about their procurement processes, so you can see some of that. And as more of these projects are announced and more of this capacity is announced, there'll be some kind of overarching metrics as well. So I think we'll start to get some of that sense of types of projects that are being installed, where they're being installed, how they're being used. We'll start to see more and more information about this. But while it is a mandate, and often people are focused on that number, the 1.3, it's almost a floor. It's almost sort of the lower limit of what's going to be installed. I mean, there's already anticipation that they're going to far exceed, what is being required of them in the states. I think we're going to see that, by the time that that mandate comes into full force and effect at the end of that mandate, I think we're going to see far more than 1.3 gigawatts installed, just because the metrics are there, the system-wide benefits are there, and I think that the utilities are embracing these technologies.
Excellent. And another question from Matt. What are the best options for point-of-use storage?
Best options for point-of-use storage. Maybe, Matt, if you have a little clarification on that question.
I would imagine he means like at your house, say, where you're going to use it, or a commercial facility, as opposed to utility scale.
Yep, I think that there's a couple of things. One is, if we saw what happened with Hurricane Sandy, Superstorm Sandy, I apologize, coming through the East Coast there, obviously very devastating. But, a place like New Jersey that has tens of, is the second largest solar installer in the country. I think they have 30 or 40,000 installs there now. A lot of those people were expecting that because they have solar, that their lights were going to stay on after the storm. It was a little bit of a wake-up call where people didn't realize that they're grid connected and the grid is their battery system. And so they did not have power following the storm. So I think one place that energy storage is able to provide a lot of benefit is you're able to use those batteries in the case of an emergency or in the case of a longer duration outage. I know in Texas, too, I believe they do rolling brownouts in Texas as well to deal with some of the peak demands. So this is a time where people who had a storage system could link that storage system up with some of their critical components in their house, the fridge, the HVAC system, and maybe not some of those some of the other loads that you have in the house, but a subset of the load in the house, and be able to keep the lights on for an extended period of time and be able to have that emergency power. So I think that that is one value to a residential customer that is good to articulate as part of this is you are able to keep the lights on when the grid goes down. As we see an increase in time of use, where the utilities put in place those basically time of use charges onto homeowners, and people, sometimes you can opt into these, sometimes you'll be forced into these. I think people are able to use their storage devices to mitigate those charges as well. So I think that that's an important value for the homeowner as well. The other part is I think that people, instead of just delivering all your solar right back into the grid and kind of going through that payment structure, people are able to capture that energy and use it themselves, basically to reduce their demand. So doing a little bit of load shifting, even if it isn't going to be, on demand all night long, people are able to reduce the amount of time that they're actually taking energy off the grid and be able to use their, say, solar infrastructure or their solar power a little bit later into the evening. So I think that there's that benefit for homeowners as well.
Excellent. We probably have time for one or two more questions. Next question was from Gordon. How do we get the right to install in the California market? Can you recommend one place where I can go to find the possible projects that are available or more information about their 1.3 gigawatt mandate?
Unfortunately, I don't think I'm the best person to answer that question on the right to install. Let me follow up, and I'll send you some information, Rick, before you send out stuff to attendees, and I'll see if I can track down a good source for that. There's a lot of information out there about the California mandate, so there are going to be dozens and dozens of sources if someone were to search, for that information. I think that is it's AB 2514-2514. So there's a lot of information about that and about the programs that are going on out there. There's definitely a lot of information on the CPUC's website as well, the California Public Utility Commission, so people can reference that for more information. But I do apologize on the right to install. I'm not positive where the best place to look for that info would be.
Okay, and we have time for one last question. This will be from John. Does the New York ISO offer dynamic frequency regulation payments? And if not, when can it start based on the FERC rule?
So the New York ISO offering dynamic frequency, I believe that New York ISO does not have a fully structured frequency regulation that pay for performance fully implemented yet. I'm going to have to reference back, so I apologize if I'm misspeaking there. But I will reference back and find out an answer to that one. I believe right now New York is going through this REV process, which is kind of re-envisioning how the grid is thought of and how the grid is operated. So they're in what is one of the most, I'd say, interesting and dynamic changes that we've seen in grid operation perhaps ever. It's definitely a very dramatic change. And so they're in the middle of that REV process right now. They're taking comments from all interested parties. So if you have a particular interest in New York, I think that's a great place to look at what's going on there. And I imagine you'll see more of these dynamic system-wide benefits valued in the Rev system, or in the New York ISO in the future as they implement some of these changes that they're discussing right now. So there definitely are dramatic changes in New York on the horizon, and I definitely encourage folks to stay tuned as to what's going on there.
All right, and that brings us to the hour, so we will wrap up here. Matt, if you have any parting comments, and if you wanted to plug your events again, go ahead.
Yes, no, I think the events are up there. If anyone has any questions about that, you can check out our website, which is www.energystorage.org, and hopefully you can find some more useful resources there. Feel free to reach out to my team and staff at any time with questions, and we'll do our best to get you a timely answer. But I would say, kind of as a closing thought, you know, when thinking about storage, it's important to think about the big benefits, kind of the big picture here. Energy storage is a bit of a paradigm shift in how we operate the grid and how we think about generating and delivering energy to end users and customers. So I encourage people to think in that big picture sense about kind of the full capability and the full potential. And there are a number of really exciting companies out there working in this space. Definitely find out more about them and our members through our site as well.
Excellent, and that's all the time we have for today. Again, our thanks to the Energy Storage Association and to Matt Roberts for presenting today. Also to Principal Solar for sponsoring the Institute. We have a few events that are upcoming. We will be at SPI 2014. Our director, Matt Thompson, will be presenting in the panel area, and also Dan Bedell will be speaking on Wednesday. So if you are at SPI, please look them up. Our next webinar is in November. You can sign up at principalsolarinstitute.org. It's an overview of the upcoming Texas legislative session as related to renewable energy. And we also posted the Dallas event for the Energy Storage Association's 25th Annual Conference.
Actually, I'll add on one more as well. I will also be out at Solar Power International doing a panel with a few technology companies and installers that is called Bottling Light. So if anyone is out at SPI, feel free to stop by and say hi at that panel. Would love to meet some of you.